let's get back here. All right. All right, so last time we were starting to talk about, we got it to this point, right? Because I remember saying carbonic anhydrase. So reactions can go in both directions, right? So we have our A and B reactants that can become C and D products, and they can go back in chemical equilibrium, and we don't have enough time to get into the K constant and chemical equilibrium, but I just want you to understand in biological reactions, you know, if we get a buildup of products, you know, a lot of those products might decay to go back to the original reactants that were making that product, because our body oftentimes might have a lot of those products. If they build up, they can get to be toxic or unneeded, and they can shunt back to the reactants, which might also be used in another reaction, okay? All right, so we have organic chemistry, organic compounds, and we have inorganic compounds. And all of you who took general chemistry was primarily focused on inorganic compounds. And I don't know, they didn't used to require that you take organic chemistry for nursing school. I know at Eastern, they required that you took this combo course about like organic and biochemistry for the Eastern nurses. And at U of M, they used to do some sort of whole kind of general chemistry thing for nurses. I don't know if the program is the same as it used to be like 25 years ago. So organic compounds are basically centered around carbon, okay? And carbon is kind of the key, and it'll be molecules of carbon in long chains of carbon, carbon after carbon after carbon. And we tend to really, basically, they are hydrocarbons. So this is why it says contain carbon and hydrogen, because it'll be carbon surrounded, being hydrated with a bunch of hydrogens. We'll look at structures, you'll see what I mean. Whereas inorganic compounds, it says here, typically lack carbon, but you know, a diamond is an inorganic compound and it is made completely out of carbon, as is graphite. So that's not entirely true. It just tends to be how they're arranged, and those carbons aren't hydrated as hydrocarbons. All right. So the inorganic substance we'll talk about first that we're always concerned with is water. And we've talked about this quite a bit. We'll talk a little bit more right now. Water is inorganic, you know, and it's probably the biggest component, most important component in your body. And it's polar. We went through that. It has the unequal distribution of charges, where the oxygen is always a little bit negative and the hydrogens are always just a little bit positive, that delta positive. And it's important because it's the solvent that all of our molecules are solvated or dissolved in our body. You know, your red blood cells are floating around basically in a suspension of water. Our salts in our body, we're not really pure water, we're more like saline solution. So we have sodium chloride dissolved in water. And sodium chloride is that substance that we looked at, that when the water molecules surround it, it pushes the sodium that's positively charged away from the chloride. And remember, all those little negative charges on the oxygen kind of encircle around and form a hydration complex around the sodium, and all the H+ ends kind of do the same thing around the chloride end. That's what keeps the two ions apart, and then they become dissolved or solvated and form an electrolyte solution. That's what an electrolyte solution is. All right. Now, water has all these other unique properties. It has all those hydrogen bonds that will hold in heat, okay? Hold in heat. And They can also take the heat away evaporatively. When the water leaves our body, it can carry the heat away with us as sweat. All right. So that's why water is such a great temperature buffer for us. All that heat in those hydrogen bonds, when the water leaves our body, evaporates, sits on our surface, it carries the heat away in its bonds. And we'll see that water is involved in a lot of the chemical reactions in our bodies. All right, just talk through that. All right, so that's the reminder here. This is what we're going to be focusing on. We should write delta right here really as the little pluses, and like a delta 2 minus over there on the O would be more accurate. This is sodium chloride when it's sitting there as a salt crystal, and you see every chloride, the big yellow ones, are surrounded on all sides by sodium. Conversely, if you look at all your little green sodiums here, they're all surrounded by big giant chlorides. And this is what I was talking about. In water, these two sodium chlorides get pushed apart, and all the negative parts of the water, the oxygens, form a solvation complex around the sodium. Similarly, all the hydrogens with their positive charges surround the chloride, and that's what keeps them apart. That's why it's dissolved. Okay, here is basically what I was just saying, the sphere of the hydration complex, okay, pushing apart the sodium and chloride from each other. All right, so again, we did this yesterday, but it's so important. So in a water molecule, oxygen forms hydrogen bonds with two hydrogen atoms to make an individual water molecule.
No.
No, and I hope you all get this now. In the individual water molecule, if we go back, hydrogen is covalently bonded to oxygen. Oxygen is covalently bonded to hydrogen. The hydrogen bonds are what happens between the water molecules, right? You guys can all remember that. That would be, you know, well, we don't have them facing each other here, but it would be like from that hydrogen, and you always draw it as like a dashed line, right? From this oxygen over to this water, okay? Loose associations, not a formal bond, okay?
Okay, so just like visually, we'll always look for the dashed line,
dashed line
and be like,
for
oh, that's
hydrogen
gotta
bond.
be
A hydrogen bond.
a hydrogen bomb.
Right.
Bond.
And you should,
Sorry.
yes, and you should be able to somewhat figure it out, okay?
Okay.
But that's what you'll see. And, you know, pretty much I will always try to have it drawn in for you. Okay, so those little dash lines are hydrogen bonds. And there will be a few hydrogen bonds you just want to remember. And water forms those hydrogen bonds with other waters. Okay. All right. All right. So now we're going to use that ionization of the hydrogen and what happens in water to describe acids and bases. Okay, so a large number of hydrogen ions, those protons, right? Remember H plus right here. H plus is just simply, I should just keep this on the draw view, right? Is hydrogen, right? And it has its one proton in the center, one proton positive, right? And then in its valence, it has the one electron. But what we did is we've stripped this electron away, right? It's gone. So now we just have a proton. So pretty often you'll always hear H plus just being referred to as a proton. Okay, chemists, that's just their lingo. That's the way they like to talk. Biochemists talk that way a lot too. Okay, so sometimes when you hear them, the proton was released, they're talking about a hydrogen ion. a hydrogen cation, I should say more specifically. And so if we have a lot of H pluses that are stripped, and we have, we have our beaker here, and we have a boatload of water molecules in there, a bunch of these, HO, all over the place. So we have, let's say, millions of these molecules. But then we get some that are dumped in that are just some H plus on top of that, in that water, put in there. Then water, which is neutral, pH is 7, suddenly we have a little bit more H plus in here than we have just H2O. We've now made an acid, okay? We've now made it acidic. Now, just a few H pluses in that water is going to make it very low concentration. But we can have a super high concentration in water. So like we know, hydrochloric acid, HCl, right? So if we put HCl, for instance, in this water, what's going to happen? Because of hydrogen bonding, you're going to separate the H pluses and the Cl minuses, right? And so all these O's are going to kind of orient around the chloride and keep them away from the H pluses. I'm sorry. I just did that backwards. Sorry, big brain fart. The H plus end of the water molecules are going to all be centered around the anion of chloride, right? Of water. And it's going to be all the O minus ends that will be forming that sphere complex around this H plus, right? Just like it did around the sodium Na plus. Do you get that? Keeping the hydrogen and the chloride apart from each other. Now, when you had sodium separated from chloride, no big deal, right? But now we have all these H plus ions. H plus, just a proton separated here. That's what makes it acidic, okay? All right, only H plus, not Na plus, not K plus, not Ca plus, just H plus, all right? This becomes a little reactive proton in the water. So the more HCl you dump in the water, the more H plus and Cl are going to separate, the more H plus is going to be kind of floating around, being solvated by that water. And because it's H plus, sometimes, we're going to swap here, is that the O is going to start forming a covalent bond with this H, and then, this will become the H plus that's free. And that's why it's acidic, because they keep swapping back and forth. So it's always reactive. Does that make more sense? People never explain this acid stuff very good to students, why they have a hard time understanding it. Okay, so again, just to reiterate, we dump our salt cube in our water, okay? Water kind of hydrates around the sodium cation, chloride, the H plus ends of the water all solvate around the chloride. But Na plus isn't going to be reacting. This water molecule here isn't going to be swapping and forming covalent bonds with sodium over the H plus. All right. All right. Okay, so acids are substances that specifically dissociate in water and release H plus. They're proton donors, okay? And usually on pH scales, acids, we always write in red, and bases we often write in blue. So I'm trying to stick with that convention, okay? All right, proton donors. We're increasing the proton content in the water. Bases are things that dissociate into hydroxyl ions. Okay, hydroxide ions can also be called hydroxyl. Oh God, that trigger happy thing. OH minus. Okay, and one or more positive ions. So we always think of sodium hydroxide being a base. So we put sodium hydroxide into, our beaker of water. Oops. Here's our HCl, how it dissociates in water. Here's how our sodium hydroxide. So you get this little hydroxyl group, okay, that's separate. So what we do then, as we get more and more H plus building up, okay, and that's kind of a tiny little number as we dump it in the water, the number of individual ions. Remember all that stuff with like Avogadro's number you probably once learned of 6.023 times 10 to the negative 23rd, okay? Because it's a small number of hydrogen ions, what we do is we put it on a logarithmic scale to give our pH scale. It's the negative log of base 10 of H plus, all right? Logarithmic scale just makes all those really big numbers or really numbers kind of scaled to the power of 10, all right? So as we increase the amount in brackets like this written around a chemical substance means the concentration, literally how much is in there, okay? So as we increase how much H plus we have, that means our acidity is going to go up. We're increasing the amount of H plus, our acidity is getting greater and greater and greater. And as you know, the more acid something is in pH, the lower it goes down on the pH scale. Because we put it, pH is the negative log to the base 10 of the content of the protons of the H plus ion. So as acidity goes up, pH goes down. Same thing with OH minus. As we put more and more base and say sodium separates from that hydroxyl ion, and the content of the hydroxyl ion goes up, we get more and more alkaline. We move away from our neutral pH of 7 and our pH goes up, all right? Now, living things like a pretty narrow pH range. Our blood pH tends to be about 7.35 to 7.45. Most living organisms grow somewhere best between a little bit, ranging from a little bit acid, 6.5, to a little bit alkaline, 8.5, okay? And we'll find, when you get into microbiology, some of them will prefer a little bit more acid environment. And so they'll tend to be places that might be more acidic in your body, like the stomach, okay? Things that like something more basic might, like to reside somewhere where we're a little bit more on the basic side, like the vaginal tract, okay? All right, so then we look at our pH scale. So things that have a high number of protons in it have a lower pH. Things that are acidic, stomach acid, lemon juice, grapefruit juice, wine, tomato juice. You can look at the scale. As you go down from pH 7 to more and more acid, this scale is times 10. So when we look at pH 7 pure water, urine, pH 6 is times 10 more acidic, okay? When we go to number 5, we're timesing by 10 again, logarithm of pH. So if anything that's pH of 5, they didn't put anything here, would be 100 times more acidic than pure water, all right? We get down here to pH 4 for wine and tomato juice. That would be, you've moved 3 away from 7, so it's 10 to the 3. Let me go back there. That would be 1,000 times more acidic. Grapefruit, 10, down to 3 would be 10,000 times more acidic, all right? Now, going up, alkaline. Things that are alkaline have greater OH, hydroxyl released, okay? So pure water, again, we have our hydroxyl, that's why it's set at 7, is exactly equal to H plus, okay? So they neutralize each other. You can see what forms here. Whoops, geez. Oh, I got to do something about this mouse. This, as you see how much H plus equals OH minus. What is H plus and OH minus? What do you think they form together?
Water.
Water, yeah. So the pH when H plus equals OH minus is pure water because that's what they make, right? They neutralize each other and form water, all right? Okay, so you can see that. Human blood, just a little bit more on the basic side. Seawater, getting a little bit more basic because it has a lot of sodium hydroxide in it, okay? So 100 times more basic. When we get up here to milk of magnesia, about 1,000 times more basic. Household ammonia, about 10,000 times more basic. And like basic things tend to be, like if you put pure ammonia, I don't recommend, but you put it in your hands, it has almost like a, kind of like a greasy sort of feel to it or slippery feel to it. So as you get more and more, all these things kind of feel a little bit slippery, you know, and acidic tends to be more and more sour in its taste as you get more acidic. Those are just some tendencies, all right? So the concentrations of acid versus base obviously affects the chemical reactions that can go on, okay? So we always keep track of the H plus or the acidic concentration in the human body. And we, like I said, we like to reside at about 7.35 to 7.45. We get excited when our patients measure outside of that range, okay? Something bad is going on. And this just reminds you that, you know, if you wanted to go and do the math and say an H plus concentration was 0.01 and you did the negative log to the 10, you know, on your calculator, you'd come out with a pH of 2. And then you could see if the H plus concentration is really, really, really super tiny, then you did the log to the base 2 and you'd come out with a pH 9. You'd actually be in the basic range there. So you can kind of play with that in your mind and it might give you a little bit better feel for it. So the pH scale runs 0 through 14. Like I said, everything representing a 10-fold difference as you move away from 7, okay? All right, and here you can see that scale as you're, you know, going from pH of 0, where you have, you know, a whole gram of H plus in a liter to, you know, having the teeniest, tiniest amount up there where you'd be using negative numbers. All right, so reiterate, pH is the concentration of protons in a solution. Neutral pH is when the number of protons equals the number of hydroxide ions. In acidic pH, you're going to have more protons or H plus cations than you will have OH minus anions, hydroxide anions. If you're basic, you're going to have more OH minus anions than you do H plus cations in your solution. So this is all that it means. Okay, here's another scale kind of showing you some more things. Some of us, you know, that one goes up and down. Some of us like to look at things vertically going across. And so that's there. Now, like I said, our normal blood pH is about 7.35 to about 7.45. So we call it acidemia when we get below that, okay? Acidemia is your blood is low. Acidosis is just kind of more the whole metabolic system, but we're not going to split hairs on this, okay? So when people are acidotic, they feel disoriented, they feel fatigued. They often will get acidotic because they've been vomiting. Your intestinal contents often become, alkaline, okay? Because we have this alkaline tide that comes out to neutralize all your stomach acids before all your food that you've chewed up and becomes chyme gets squirted into your small intestine. We have to start squirting out a bunch of basic stuff from, say, like your gallbladder, so that we don't acidify and burn up our small intestine. All right. So when you start vomiting all this acidic alkaline contents up, you become more acidotic. Diabetes. When we get to that, maybe we'll get so that you can understand why sometimes people with diabetes will get into what's called DKA, or diabetic ketoacidosis. Okay. That's going to be putting a bunch of stuff together. Sometimes people have lung disease and they can't blow off all of their carbon dioxide waste. Well, carbon dioxide waste that can't be blown off becomes carbonic acid in our blood. And so that ends up making us a little acidotic. We also can get alkemic, or alkalemia, alkalosis. Okay. So your blood pH tends to get a little bit above that 7.45. So about like 7.5, maybe into the 7.8 range. And
I got
these
a quick
people,
question.
yep.
I'm just wondering, I'm a practicing nurse right now.
Uh-huh.
So it's interesting that in a COPD exacerbation where the patient is becoming more acidotic, they're becoming more lethargic, where a patient who's in DKA is becoming acidotic as well, but is so much more violently ill.
Right.
But they're both.
Yes. And this gets into the nature of one being a respiratory acidosis and the other one being a metabolic acidosis.
Yep,
And so metabolic acidosis almost always tends to be worse because it's more profound through the whole entire, all the cells of the body. So yeah, we'll get into that. That gets into more complex physiology that, sometimes we don't really even get into as much. So, and a lot of times what we do, we will say sometimes we correct a metabolic acidosis with it temporarily by trying to institute a respiratory alkalosis while we're waiting to correct metabolically all the acidotic stuff. So you'll see that, like, your patients in DKA, while we're giving them sodium bicarb and all that stuff, we're also maybe like, ventilating them to try to get them to have a little bit of a respiratory alkalemia going on to also help take care of that. So yeah, it gets pretty complex. The whole acid-base management of patients is one of these really difficult things. Okay, so you can get alkalotic or metabolic respiratory or metabolic acidosis and alkalosis. So people, when they're alkalotic, they get to feel dizzy and agitated. This is like what happens to all those crazy people who decide they're going to climb Mount Everest, and they get into that high altitude breathing. There's low oxygen tension, and, you can, you end up with respiratory alkalosis. It's going to be hard to explain and have you understand that. Other times, if you vomit stomach acid, it hasn't gotten down to the point where you're vomiting up the alkalotic contents, you're actually vomiting your stomach acid out, or sometimes people take too much Tums products, things like that. They can get an antacid induced alkalosis. Normally, a little bit of that getting out of range, your body's homeostatic mechanisms kick in and help regulate the pH. But sometimes we get so far out of range that that's when the whole medical team has to come in and intervene. Now, in our body, we have some natural buffers. And buffers are chemicals that help resist some of these pH change. So even in your blood, you'll find like your proteins are a little bit basic on the ends of them. So your blood proteins can kind of cling to and pick up and buffer some of those H+ protons that are moving around. But, you know, again, at a certain point, you overwhelm your buffers that can absorb those H+ protons. So that's, you know, that's again, when we have to intervene. Okay. All right. So when we get into our organic compounds, we'll talk a lot about the structure of the organic compounds. Now, again, reminder, organic compounds means we're dealing with long chains of carbons that are hydrated. This is not the same meaning in common parlance that we use when you say you're buying organic food at the grocery store. That just is to mean like natural, without hormones, pesticide treatment and such. And really half the time, even that doesn't mean much because it's not very well controlled by any sort of regulatory agency. You know, I laugh sometimes when I see things like bags of chips and that with the label organic on it, trying to convince people somehow that it's healthy. All right, so we get our chain of carbon atoms all linked together, and we call that the carbon skeleton of our organic compounds. And so most of the chemistry we're going to be paying attention to are our organic molecules. Most of those carbon compounds will be hydrated with hydrogen. Sometimes we get like long substitutions off of that. We remove the hydrogen and we'll find some substituted side chains. We tend to call these R groups. We'll look at that. Some of our smaller hydrocarbons will be able to dissolve somewhat in water. And you know this, it's a lot easier to dissolve your salt in water than your sugar in water. You know, sugar is going to saturate the water a whole lot faster. Do that as a little experiment at home if you want to try it. But, you know, sugars are really small carbohydrates, simple sugars. So they have a little bit easier time solvating in water. When we get big, long carbohydrates, we're probably going to have to solvate them in organic liquids, like dissolves like. All right. These never form, obviously, electrolytes. We call all these organic compounds non-electrolytes. Electrolytes are going to be things like the simple sodium and chlorides that separate. They remain there in their cation and anionic state, and they can actually have a charge pass through and carry electricity, which is, you know, what you know when you're supposed to be avoiding being in standing water when there's lightning, right? Our inorganic molecules generally are not made of carbon and hydrogen together, these long carbon chains. And they usually do dissolve in water and they form ions in water, thus being electrolytes. So examples for these are going to be oxygen, carbon dioxide, and all those inorganic salts like sodium chloride, potassium chloride, etc. All right. So water, all of its unusual properties we've been discussing. It's the most abundant compound in living material. This is what I say, we're always searching for it on Mars for the presence of life, and will life be able to be supported on that planet. It's 2/3 approximately the weight of an adult human. Most body fluids are made of it. A lot of our metabolic reactions use it and consume it. And, you know, we already talked about how it transports heat in our body. It's also like, you know, when it's cold like this, think about water. The big unusual property of it is it's the only substance, I think, that expands upon freezing. And that is also due to the hydrogen bonds. And that's why we can sustain life through the winters, and why life could evolve on Earth through all the coldness in that is because we get that insulating layer of ice with still water flowing underneath in our rivers and lakes so that the fishes could swim right around in the water below. And eventually they could evolve into things that could walk out on land. Let's not forget oxygen, because oxygen is obviously going to be an important inorganic molecule. We use it to release energy from nutrients. We basically combust our food, combust our sugars, but we do it in short little pieces of metabolic reactions rather than taking a lighter and just combusting it. Okay, and we capture the energy in all those little short metabolic reactions instead of just burning it up and burning up all of our food in us. Carbon dioxide is our main waste product. And as we just talked about, we blow it off to the environment. Okay, we get rid of it. And the plants will use it. The plant's waste product is oxygen, and we use that. And that's why we're in trouble when we start plowing down the rainforest, right? Because that makes the oxygen for our atmosphere. Of course, we also have all those inorganic salts that are necessary sources of ions. You know, sodium chloride obviously plays a big role. We'll see also that things like potassium and calcium play big roles. All right. So we'll see that with our action potentials, things like that as we move along. Every time I click somebody coming into the class, I end up also clicking somehow out of these slides. All right. All right. So organic molecules. These are a bunch of organic molecules. So you'll see how they contain these long chains of carbon. And as I say, they're hydrated over and over with hydrogens, but sometimes they also are hydroxylated with OH- ions as well. This is basically a simple sugar. This is the same sugar drawn. This is it drawn as an open chain. This is it being drawn with it kind of folding back and being in a 6-carbon ring. And here it is without all the additional, little carbon hydrogens drawn on it. You can see it down here. Again, the monosaccharides. We'll see how we put the monosaccharide units together to make disaccharides and link them together to make long polysaccharides and starches. Carbohydrates, carbon that's hydrated. Okay, these are the main sources of all of our cellular energy. So it supplies the raw energy materials that help us build cell structures. Like I said, most of these small ones, carbohydrates that we use for energy, they're small enough to still be water soluble because they have lots of protons they can release and lots of hydroxyl ions. Okay. Carbohydrates contain carbon, hydrogen, and oxygen, and they usually contain them in a pretty specific ratio of hydrogen to oxygen that's usually 2:1. All of our simple sugars basically are isomers or have the same form as a structural formula as glucose of 6 carbons, 12 hydrogens, and 6 oxygens. So you'll see all those different monosaccharides have that same formula. They're just arranged differently. And then things get a little tricky that we have a bunch of functional groups that can get added on to all these carbon chains. So our little hydroxyl group, our OH, when we add them onto our carbon chains, 1 carbon being the simplest, that's what makes something an alcohol. So that is methanol. When we add on 2 carbons and we just have the 1 OH group, it's the next biggest alcohol, or the second smallest alcohol really, of ethanol. Quite a difference between ethanol you drink and methanol that you might put in a vehicle. This is toxic poisoning to you. This also is toxic poisoning, but at a much higher level. Isopropanol, also isopropyl alcohol. This is the 3-carbon alcohol with the OH on the middle carbon. Okay, and you know that for cleaning your wounds. All right, so an OH group is an alcohol group, hydroxyl group. When we have a carbon double bonded to an oxygen, it's called an aldehyde when the other thing bound to that carbon here is a hydrogen. If you have a chain of carbons and this double bond of O's is appearing like in the middle of a molecule, these R's mean carbons attached to other stuff, carbons attached to other stuff, then it's called a ketone, all right? When you have a carbon that has 3 hydrogens surrounding it, we call that a methyl group. And when we put an amino group is an NH2 that's bound to the carbon, that's amino, all right? This is an ester group that's like that ketone, only instead of being bound to a carbon and bound to other carbons, it has this other oxygen bound to it. Ether is an oxygen appearing in the middle of a carbon. Sulfhydryl is a lot like the OH group, only it has an S, okay, a sulfur group instead of OH. Carboxyl, this is one you really want to get to recognize. This is also written out as COOH all the time, but it's a C that's double bounded to an O. And instead of like up here being bound to an O and then more carbons, it has the alcohol and the double bounded O at the end of the molecule. Oh, and then the phosphate group is a phosphorus, a P, surrounded by oxygens, okay, double bonded there. Do I want you to memorize all those? No, kind of get some feel for it because obviously I'm not making you memorize anything, but you know, kind of get a feel for these different groups a little bit. You know, we can only do so much in this class on chemistry, but you're going to need to learn to identify how some of these main functional groups work. And that's why I say pay attention to the amino and the carboxyl group, because the two of these will surround a carbon and they form amino acids that we use to build our proteins. So we have a carbon in the center that we call our alpha carbon. And this is going to have R, always means just a chain of other carbons. All right. We have an amino, NH2. Okay. It's an ammonia group, basically. And then we have that COOH, a C double bonded to an O and an OH. That's our carboxyl group. All amino acids will have this. We'll have this around the central carbon. Have an H up here. And where they change or vary, what makes the different amino acids is all the different junk that makes up this R group. The smallest one being glycine is just another hydrogen, okay? All right, and the reason we get to know these is we're gonna take our small organic molecules and we're basically gonna stitch them together or knit them together and make them into bigger macromolecules. We're going to take amino acid plus amino acid plus amino acid and make proteins. We're going to take sugar plus sugar plus sugar plus sugar, and we're going to make disaccharides, polysaccharides, carbohydrates. All right. So the macromolecules that we're going to make, the carbohydrates, the proteins, the nucleic acids, are going to be polymers of repeating units. The smallest unit, the repeating unit, will be a monomer. So our carbohydrates will have monomeric units that are simple sugars. Our proteins will have monomeric units that are amino acids, okay? Our lipids don't have a monomeric unit, and you'll see why in a little bit, okay? So don't think that fatty acids are the monomeric unit. Don't get confused by that. We'll just say that from the beginning. Monomers join together by dehydration synthesis, also known as condensation reactions. When you have sweetened condensed orange juice, it's just a concentrate of the orange juice where the water's been removed and you add the water in to make it. That's the same thing here. It's a condensation reaction. We're going to remove water from our substances to condense them together, okay? Dehydration synthesis. Dehydration, another way of saying remove water. So we're going to take A plus B, and we're going to combine them to make AB. So in a dehydration synthesis, also known as a condensation reaction, A or B, one or the other, is going to have something like an OH on it, and then an H on the other molecule. And we're going to remove the OH and the H, which you can see is water, right? And form a new bond. So what we're going to do here, when we go to draw this in, we're going to be removing water right here, okay? And we're going to take and draw a new bond from this carbon over to this nitrogen. Okay, so as you can see, right here is that new bond, carbon to nitrogen. Here's the water that's been removed. Everything else is the same. HHN, the amino end in this case, right? We have the C and the H and R, that R group up here. We have our sort of ketone or carboxylic acid right there. We have our amino group right up over here. That's your amino part, right? This was the amino here. And then all this is also the same, okay? So that's going to be our bond in that condensation reaction. Hydrolysis, when we do hydrolysis, is just the reverse. It's taking our macromolecule, we're going to put the water back in to break up the bond that we just made. So if we went back here, we would take this water right here, and we would literally say that water would attack this bond right there, and it's going to attach itself back and push the reaction in the opposite direction, okay? And so then we would be adding one of these H's down here on over here, and we would be adding back this OH part over here back to over here, and we broke apart that bond right there, okay? It's just the reverse. Water attacks is going to break this bond. We've added an H and an OH, okay? We took the macromolecule that's bonded here, the water comes in, attacks it, and we're going to add then with this oxygen right here, get rid of that, we'll draw it down here, OH, and now we have a H added on over here too, okay? And you see that right down here. All right, I know it's hard, and we go through it fast. Okay, so carbohydrates are going to be the main sources of our cellular energy. The small ones, like I said, are water soluble. They're called carbohydrates because they contain carbon, hydrogen, and also oxygen, and always in that hydrogen to oxygen ratio of 2 to 1. And you'll see the small isomers of glucose are C6H12O6. You can often multiply these like by 2 and see that it would be C12H24O12. That should make you recognize a carbohydrate formula right away. So the monomeric units are going to be the monosaccharides, the simple single sugars, glucose, fructose, mannose, going on and on. they'll combine to be disaccharides, which will be sucrose, lactose. Sucrose is a glucose plus a fructose, okay? I'm not going to make you memorize all the components of that. Just recognize that it's two sugars together when you see it. And then polysaccharides. And the point from which you get to being a polysaccharide to actually getting up to being a big enough polysaccharide to be called a starch or a glycogen is really, not that important. All right. So carbohydrates sometimes will be involved in our cellular structures. They aren't going to exactly form the cell wall or anything, but we'll see them embedded in the cell wall. And sometimes they can be even antigenic. All right. Many of these are isomers. Like I said, isomers of glucose. They have the same formula, C6H12O6, but they're just arranged differently. So you can see that here. Here's basic glucose. You see the difference is just kind of the flip side over for galactose. Okay, they're almost a mirror image in that sense. Fructose. This you can see at the end is what we call an aldehyde group, a CO with an H at the end. Here, that O, that little C, some people just say equals O here in the middle, is a C double bonded to an O with other carbons attached on both sides. This is arranged as a ketone group. Okay, so a ketone and an aldehyde behave a little bit differently. All right, so monosaccharides will be simple sugars that have anywhere from 3 to 7 carbons. Glucose, deoxyribose are some examples that we'll be using a lot. Glucose here, again, fructose, because it has that ketone when it circularizes, is its ring formation is a 5-carbon ring as opposed to the 3-carbon ring that glucose and galactose and all those others make. Here's galactose again. And disaccharides, when we hook them together, again, they are knitted together, the monosaccharides, through our theme here, dehydration synthesis, condensation reactions. We remove water, okay? We remove water and we form our new bond. Here's the water left over here. If we wanted to break apart this disaccharide of sucrose, we'd have to have the water come in and attack this bond, reverse it back, and we come back to our glucose and fructose. So condensation, dehydration synthesis, building everything together in one direction to make our macromolecules. Pyrolysis splits it back apart. And we do that same reaction. Monomer, I don't know what that is. That's somebody else. Okay. Monomer to monomer. Is somebody trying to, Aaron, I think. Aaron, you're putting up here. Are you trying to talk? I think you just need to turn off. All right. So one disaccharide, and then we start hooking on more monomers, and we start building polysaccharides with dehydration synthesis reaction after dehydration synthesis. So it hooks on and we become a polysaccharide, a long chain of monosaccharides. And then we can even start branching and building chains, going off of chains in different directions. And so we start making our starch, okay? All right, we have branching, they're called branching enzymes that actually make all these branches of the disaccharides, linking on to more monosaccharides in different directions. All right, now lipids are a little bit different. Lipids will also consist of carbon, hydrogen, and oxygen, but not in that same sort of hydrogen to oxygen 2-to-1 ratio. All right, we'll see how they're different. Our lipids are going to include triglycerides as one type of lipid. Our phospholipids become really important for making our cell membranes. And then we'll also have the classification of these ring formation of lipids that are steroids. Lipids, obviously, with phospholipids, you've learned the phospholipid bilayer is the primary component of our cell membranes. And all those phospholipids are made largely of carbon, hydrogen, and oxygen, to which at the end, we have those phosphate groups, that P with all the O's surrounding it, at those hydrophilic heads, all right? The long tails off of those phospholipids are all those carbon-linked, carbon-linked, carbon-linked carbons that are hydrated, that are our fatty acid tails. So these lipids, as you know, are, if ever you tried to make salad dressing and you put oil in water, nonpolar, okay, all that carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, they're, you know, not charged. And so they don't first mix in with the water, right? You can't get it to kind of solvate. It just kind of breaks up into little bubbles of oil that then rapidly coalesce back to little individual glob of oil. Because it's, as I always say, like dissolves like, it is not charged. So it doesn't solvate in the water. And usually lipids are less dense than the water, so they float on top. If they were more dense, they would sink to the bottom, okay? The most abundant lipids in our body are triglycerides. This is how we store our fat. So when you're looking at your, you know, your butt, your hips and all that, primarily you got cells that are full of triglycerides. And this is our reserve source of cellular energy, okay? These contained fats will burn up and contain more kilocalories per unit of fat than do carbohydrates or proteins. You'll see it's 9 compared to 4 or 5, I can't remember. Anyway, so they contain carbon, hydrogen, and oxygen, but have a much lower oxygen content than do the carbohydrates. And we'll see that our triglycerides contain one molecule of glycerides to which we'll attach 3 fatty acids, all right? When we made our phospholipids, we're going to have 2 fatty acid tails and a phospholipid head. All right, so the basic simple formula here when we're looking at our lipids will be, we have glycerol, so a 3 carbon unit here that's hydrated, except hydroxyls on each carbon, all right? To which we will attach a big, long fatty acid tail. So fatty acid tail is a big, long carbohydrate chain, hydrocarbons, okay? All these hydrated hydrogens on carbons. At the top is a carboxyl group, that's CO double bonded and an OH. And guess how we're going to link our glycerol to our carboxyl group? You got it. Another condensation reaction, right? Or dehydration synthesis. All right, so when we do that, let's go back here. Let's just look. Dehydration synthesis, right? We're going to remove water. And then we're going to have this attached on here plus water. And you're going to do it 3 times over, okay? And when you remove that water, you've removed the H that was up here and the OH that used to be down here, right? Okay, so that's how you're getting there. Take that off. And now you've linked 3 hydrocarbon chains or fatty acid chains to a glycerol molecule. So when you see the glycerol, 3 fatty acids, this is what is a 3 fatty acids glyceride. This is a storage form of fat in your body by and large. When I look at this one and this one, and I see all of this is just carbon, hydrogen, carbon, hydrogen over and over and over again. And we name them based on how many carbons are in the chain. This one is palmitic acid. So it's got 15 carbons. This one is stearic acid. It's got 17 carbons. This one is a little bit different. What we did in here is you throw in this kink, okay? And it's kinked because instead of having all of our carbons completely hydrated, we have a double bond here. This double bond is what makes this one unsaturated. All these carbons are completely saturated with hydrogens. There's no double bonds. This one you can see is a cis hydrocarbon. Let me get the thing here. Okay, it's on, the hydrogens are on the same side of the bond. If it was trans hydrocarbon, we would have the hydrogens, the kink on opposite sides, okay? So cis just means same side and trans means opposite side. And you can see that now when we talk about gender, we've used the language of chemistry kind of to describe that. When you identify your biological genitalia and your mental philosophy of your gender to be the same thing, we say that's cisgendered. When they're different, transgendered, okay? And maybe, you know, knowing that, one helps you understand the other a little better. All right, so we talk about saturated and unsaturated. So saturated, like I said, is just going to be no double bonds, okay? Saturated fat is an example, butter, delicious, right? Saturated fats tend to be solids at room temperature, often of animal origin. Unsaturated fats, this one we would say has two double bonds, so it would be polyunsaturated, okay? So they show olive oil here. This is actually incorrect because olive oil is actually a monounsaturated fat, but you get the gist of it. So these unsaturated fats have at least one double bond. They tend to be liquids at room temperature and more often plant in origination, okay?
So I have a question.
Yep.
When, let's say you're buying like coconut oil and you see that it's solid at room temperature, and then they have another form that's liquid at room temperature, does that mean they've made it into an unsaturated fatty acid?
There should be, yes. And coconut oil has some unique things to it.
Okay.
That will be a good way to start the next class because we're right here at 11:30. But yes, liquid, if it's liquid, and coconut oil has some what we also call short chain fatty acids. So the shorter the chain, also, the more likely you can get it to be a little bit more liquidy. The longer the chain goes on, the more likely it's going to be solid. So there's, you know, we're oversimplifying everything because we can't get into the great big details of it all right now. Yeah. And I know coconut oil is super popular for health these days. You know, it used to be a thing that was way, you know, back in the 70s, you know, coconut oil, the only thing you could use it for was to slather on your body and go out and deep fry yourself underneath the sun. So I think it's actually fairly healthy. So I wouldn't be too afraid of coconut oil. I use it myself to cook. All right, so I'm going to close for now, and we'll talk more a little bit about coconut oil next time. And I know it seems like we're getting behind, but we couldn't just separate the schedule off everywhere it was. And I will see all of you in about an hour. I'm going to jump in the car and drive to Ann Arbor. Wait for me. If I'm late, I hope I'm not. I don't think there's any real snow problems or anything right now going on. Okay. All right.
Roads
Guys
are
have-
fine.
All
We're
right.
good. Have a good